Applying Gen AI for drilling optimization and insights from a real world implementation. I'm Bethany Fisher, digital editor of World Oil, and I'll be your moderator today. Drilling activity generates a significant amount of data. This data is typically captured across a variety of sources, such as time and depth series data from geological surveys and drilling operations, unstructured data from end of well reports, and structured data from internal IT systems. To date, synthesizing this data into a usable format and generating actionable insights has been a challenge. In this talk, we present results from a fielded Gen AI solution that synthesizes data from historic drilling wells in Romania and provides a natural language interface for drilling experts to interact with. Additionally, it provides recommendations for optimizing well design and performance parameters based on past results. Our goal is to reduce project costs by streamlining information discovery and improve decision accuracy by leveraging data-backed insights. Joining us for today's webcast are Anthony Martin, Senior Advisor of Global Skill Pool Well Engineering from OMV, and Jeff Washburn, Vice President from DeepIQ. Anthony Martin is a Senior Advisor of Global Skill Pool Well Engineering at OMV for the past 5 years. Before joining OMV, Anthony spent several years as a senior directional drilling engineer at Halliburton, where he demonstrated exceptional leadership and technical skills in optimizing wellbore placement and trajectory. His deep knowledge of well engineering, combined with his strategic mindset, allows him to identify and implement cutting-edge solutions to maximize efficiency and minimize risks. Anthony has a proven track record of delivering successful projects on time and within budget. Jeff Washburn is a seasoned IT professional with over 25 years of experience in the industry. He is currently the vice president at DeepIQ, a company that provides AI-powered solutions for the energy sector. At DeepIQ, Jeff oversees the development and delivery of innovative products and services that help clients optimize their operations, reduce costs, and enhance safety. He also leads a team of talented engineers, data scientists, and domain experts who are passionate about solving complex problems with cutting-edge technology. Prior to joining DeepIQ, Jeff was an architect at SLB, the world's leading provider of technology for reservoir characterization, drilling, production, and processing to the oil and gas industry. Just some general housekeeping notes before we get started. Following the presentation, we'll have a short question and answer session. You can participate in the Q&A session by asking questions at any time during the presentation. Just type your question into the Q&A box located on the bottom left corner of your screen, then click the submit button. Please take this time to familiarize yourself with the webinar platform. At the bottom of your screen, there are multiple application widgets you can use. All of the widgets are resizable and movable, so feel free to move them around to get the most out of your desktop space. You may enlarge the slide window at any time by clicking on the arrows on the top right corner of the slide area. The slides will advance automatically throughout the event. If you are experiencing problems with the program, please press the F5 keyboard to refresh your presentation. You can also visit the webcast help guide by clicking on the help button below the slide window. Now let's get started.
Great, thank you very much, Bethany. Hello, everyone, and thank you very much for joining us on this webcast. Thanks also to Anthony at OMV for doing this and to World Oil for making it happen. We're here to talk to you about an exciting technology that was deployed at OMV. So the problem we faced is that well design is very complex and a very time-consuming process. And it involves multiple parameters, constraints, and uncertainties. It requires a lot of data analysis, engineering expertise, and of course, trial and error. Moreover, it's often difficult to leverage the knowledge and the expertise from your previous wells, especially when they're located in different contexts or geologies. So the solution we developed at DeepIQ is a novel approach, and it combines 3 components: a knowledge graph, a context-aware, trainable offset well system, and a machine learning-based well-designed optimization system. You'll get a chance to see these throughout the presentation. These components work together to provide a powerful and an intuitive tool to help us design wells faster and cheaper. This is enabled by the natural language interface, which is powered by our powerful Gen AI technologies. As you will see, the solution is a game changer, and it will enable us to leverage our data and our knowledge more effectively, to design better wells more efficiently, and to achieve our business goals more successfully. Anthony, do you want to talk to us about purpose and objective?
Yeah, absolutely. Hello, everyone. So what we wanted to do was showcase this OMV and DeepIQ case study that we did under the Digital program within OMV. We want to demonstrate the value addition that we can actually gain from this, having this more robust tool set to improve the overall landscape, and also look at the direction and potential of data analytics in oil and gas.
Okay, great. Thank you very much. So let's go ahead and get started and introduce the project a little bit. Anthony, tell us a little bit about OMV, please.
Sure, yeah. OMV founded in 1956. This lovely German word here just basically stands for the Austrian Oil Management Corporation. 413th largest public company in the world. We're active in oil, gas, upstream. We're also geothermal and low carbon business, as well as petrochemicals and plastics recycling. And over here, we're pretty much the market leader in Central and Eastern Europe.
Great, thank you. So a little bit about DeepIQ. We are a no-code AI-powered platform, and we've built our tools to automate industrial intelligence. Our highest goal is AI-driven automation. Can an AI algorithm automatically run a drilling rig without a human in the loop? Well, we see this as an incremental journey. Today, we provide significant acceleration and accuracy improvements in the industrial digital programs. And the number of subject matter experts like drilling engineers or geoscientists required to execute them. We do this, sorry, here we go. Oh, wait, sorry, this went out of the way. Let me put it back. Here we go. We do this by solving three different problems. One, sorry, I'm not sure why the slides are moving by themselves, but they seem to be. Number one, extract, which is the automated ingestion of geospatial and time series data into cloud platforms. Two, converting these data sets into high quality data models, which are amenable to machine learning and exploration, leveraging our modern cloud data platforms. And three, generating insights from these data using generative AI and knowledge models. DeepIQ is a team of AI experts, and we've spent our careers leading industrial digital transformation. We're based out of Houston, Texas, and India. Anthony, would you mind talking to us about the problem background?
Yeah, sure, absolutely. So obviously we get so much data from the drilling activities, and they're captured across various sources, whether it's the real-time operations center, which is gathering them, the live stream from the rig itself, the daily drilling reports and our reporting system, end-of-well reports, and after-action reviews are just some of them. We have these operational and non-operational variables which are captured within the system. But because there's so much time is required for this data collection, when we actually look at it for offset well analysis, it takes a huge amount of time to go through all this, first to find them, then to go through them, and then to make a judgment on them for our offset well analysis. So the goal for this was a solution that unifies and interconnects all this data to support the drillers in the planning and running operations.
Okay, great, thank you. All right, so let's jump into where the data came from. So drilling engineers often need to make decisions on how best to drill into the Earth's crust so that they can access the oil and gas. They need to do things like, how do you construct drilling plans, evaluate drilling sites, or estimate drilling costs? The issue is that drilling data is spread across multiple sources like file systems, time series, depth series databases, and other unstructured reports. So to leverage this historical data in decision-making, drilling experts need to manually pull it all together, often use spreadsheets to complete their analysis. For example, when you're designing a new well, Data extracts from drilling reports, geological reports, end of well reports, all need to be gathered, cleansed, matched together, and then somehow get into Excel. This is a very cumbersome process, and typically the engineers only often analyze a fraction of the data to generate their insights. For this program, we used advanced data engineering and machine learning workflows to bring this into a single unified data model and then enable analytics at scale. We used rinse and repeat workflows that are now available to augment this analytical system. So when we augment with additional wells as newer data becomes available. Now, OMV's got a wealth of drilling data. The goal was to maximize the value of existing data and simultaneously build a framework that allows for more data to be added easily. So you are looking at the high-level solution architecture. Starting at the bottom and working up, we first ingested data from multiple sources in multiple formats. This included data hidden in PDF files, time series, depth series, data exports, APIs. The data was ingested into an as-is staging environment in the data lake. Next, data engineering workflows were used to construct a custom knowledge graph specific to drilling domain. And I'm going to talk a fair bit about knowledge graphs. If you're not familiar with them, a knowledge graph is a way of storing and organizing data that shows connections between different things. For example, a knowledge graph that can show that Austin is the capital of Texas and Texas is in the state of the USA. And the knowledge graph can also display complex relationships, such as what are the main attractions in Austin. Google uses this knowledge graph to store relevant facts and images and links when you Google something on the right side of their screen. So the drilling knowledge graph seamlessly integrates all these different data sources. It also promotes an understanding the interconnected entities, properties, relationships within the drilling data. So we have things like wells, location, bits, etc. Finally, the knowledge graph feeds this generative AI-powered natural language interface so that our drilling engineers can now extract insights without requiring advanced data skills. Additionally, it powers a machine learning-based analytics layer, which does empowering drilling engineers to optimize well design. All right, let's jump into the DeepIQ solution and what it is that we built. So you're looking at the overall flow of the data movement within the analytical solution. As mentioned, data is initially directed into a data lake, which feeds this knowledge graph. The knowledge graph then supports two things: context-aware offset analytics and a generative AI natural-based interface. Within the context-aware offset analytics layer, there are two significant components. The first component, you can choose offset wells according to your specific needs and employ a multivariate trainable machine learning methodology. With that second component, you can then examine the data from your chosen offset well using machine learning techniques to drive valuable insight. I'm going to give you a demo of this in just a few minutes. Let's go ahead and jump in just a little bit more on these different components. The first is the knowledge graph. All the data is ingested into this knowledge graph. So this drilling knowledge graph represents the drilling domain and entities, their properties and their relationships. So let me give you an example. Let's say we've got well A, and well A is located in the Gulf of Mexico. We know that it has a depth of 10,000 feet, that it used a rotary steerable system, that it achieved a rate of penetration of 150 feet per hour, and that it encountered a stuck pipe problem due to differential pressure. All of this data gets put inside the knowledge graph and can be used to help design future wells. So data engineering and machine learning workflows were used to extract and persist the relationship from the ingested data into the knowledge graph. This graph serves as a highly curated data layer that feeds this higher order analytics and our natural interface for the drilling engineers. So we can now access, integrate, and query the data meaningfully. It also allows us to discover new insights and patterns from the data we might not have noticed otherwise. It is used to communicate and share our findings with others that are intuitively and understandably. So let's talk a little bit about our context-aware offset analytics. So typical offset well analytics software calculates offsets with a very small predefined set of wells. these offset calculations are predominantly driven by distance from the reference well, which is fine, but not very comprehensive. The offset wells you want to consider will depend on the decisions you're trying to make. For example, if your use case is to compare cost of 2 or more wells, well location, trajectory parameters might be very useful for that. On the other hand, you might want to select the optimum BHA or bottom hole assembly, which is the lowest part of the drilling string. You should focus on lithological properties, which are the physical characteristics of rocks, in determining your offset wells. So the context-aware selection allows you to choose whichever parameters are relevant to your current analysis. The properties can be different types, like numerical, depth, categories like field, or a sequence like BHA or lithology. Once you choose the parameters you like and the corresponding weights you want to assign them, the offset calculation uses this multivariate offset similarity calculation to incorporate all of the desired parameters into determining your offset wells. Finally, once we have further examples, you can now use machine learning to teach the system to identify offset wells. Okay, so this is some exciting stuff here. So machine learning-based well design optimization. Once you've got your offset wells that are selected, we can now cluster them so that offset wells with similar characteristics can be separated out. Clustering is an unsupervised learning method that groups data points based on similarity. It helps us find meaningful patterns and structures and categories in unlabeled data. So the clusters of well or individual wells can be compared to identify how well-designed parameters impact your KPIs. Pareto plots can be used to understand trade-offs. We'll see this in the demo. The fundamental idea is that design decisions typically cannot make one individual outcome better without making another worse off. For example, increasing the drilling speed might be associated with higher hazard risk. The goal of the Pareto optimally plots is to identify well designs. For example, wells with a lower cost per meter and lower time per meter than their peers are ideal candidates for further consideration. In Pareto terminology, these are called non-dominated solution. We'll see an example of that in the demo. Okay, so what was the process that we followed for this? So a drilling engineer like Anthony will specify the parameters, things like location, geology, trajectory, and other relevant properties that are tailored to their needs. The offset well calculation generates an initial set of offset wells. Now you can fine-tune the selection by modifying weights or giving feedback to the suggested wells. You then identify the different wells of interest. You can leverage clustering algorithms and ranking plots to pinpoint the design specifications or identify risk factors with the highest probability and the corresponding mitigation strategies. The drilling engineer will provide feedback on the model results. This feedback is then used to retrain the model, making the model more accurate over time. Okay, so before we jump into the demo, I want to talk just a little bit about our generate AI-based information retrieval. As you know, Gen AI has become really popular, and it's a great tool, but what it does is it creates new content from existing data. This is brilliant for generating text or images, videos, or code, but how can it help with a critical business application? Well, typically, Gen AI has the problem of hallucination. For example, if you experiment with questions about drilling-related data objects, you might get responses about production, which are wrong. DeepIQ's Gen AI tech avoids this hallucination problem by using a completely different approach. Instead of generating content from scratch, DeepIQ's technology retrieves information from this highly curated knowledge graph. So when a drilling engineer asks Gen AI a question, it's not generating an answer from scratch. Instead, it's searching through the knowledge graph for the most relevant and reliable information that matches the query typed in. It then presents the drilling engineer with a concise and coherent answer that only has the necessary information. Furthermore, it gives complete lineage into what knowledge graph entities were crawled to respond to your query. This means that we can see where each piece of information came from, how it was processed, and how it was related to the other data. In this way, we can verify the accuracy and relevance of the answer and trust its quality. So at this point, Satish, I'm going to ask you to go ahead and share your screen, and let's jump into the demo. Once again, folks, if you have any questions, please type them into the little Q&A, and we get towards the end, we'll be happy to answer questions. Okay. Just waiting on Satish there. Satish, are you able to share?
Can you see my screen?
Oh yeah, perfect. It's in my little window here. Okay, thank you. Let's go ahead and get started. You're looking at the DeepIQ Drilling Analytics app. This app aims to bring machine learning into the process of well drilling optimization. So the demo environment is built with simulated data with a small set of well properties to protect the confidentiality of OMV's data. On the left, you can see a pane where you select options for the offset well analytics. On the top, you'll find various options to visualize and analyze the offset wells. As we mentioned, OMV has a ton of data, and it's spread across multiple data systems. With this new app, you've got a single stop for all your data for these wells of interest. In the center, there's a map. The map currently shows all the wells we have in the data lake. Let's take an example of an existing well as a reference well first. Satish is going to pick one of the Wildcat Frontier wells from the reference list. Okay. Now that you have your offset well selected, you can do context-aware analytics by deselecting the properties and changing the importance of the features. For example, you may wish to alter scoring. If you're not interested in the mud score and do not want to include mud in the similarity scores, you can disable the mud score, as Satish has done. You can now specify which well properties to include and which ones to exclude. For example, you might want to include only certain section diameters and exclude some of the wells from a field. Satish is showing these features. As you can add additional filters as required. All right, so Satish is making a couple of changes there. Once these changes are done, the offset and reference well list will then be updated. That's great. Thanks, Satish. All right. We can now move to our well descriptive plots, assuming you're happy with the offset wells and their properties. All right, here we go. Here you can slice and dice the data any way that you want to. There are multiple ways to visualize this data. You can plot data for single wells or multi-well plots or multi-well summary plots. A sample plot here shows the average cost per meter for all the offset wells across the fields. So let's have a look at our heat map plots. Thanks, Satish. The scores are divided into 3 categories, which you can see on the screen. On the left, we have our geology. In the middle, we have our design. And on the right, we have our technology. In each of these plots, similarity scores of the reference well with an offset well are shown with the well with the highest scores being on the top. Perfect, thanks, Satish. All right, so now let's move on to machine learning on those offset wells. This is done in our clustering tab. Perfect, thank you. You can see the reference well in the upper right corner. Satish will hover over that. You can see the reference well scores and also all the wells in the same cluster. So a little background here. We compute similarity scores in the multi-dimensional space. The similarity score is then projected onto the 2D space. We do this for 2 reasons. The first one is that it reduces the noise in the data. And the next is that it allows us to look at the offset wells in a low dimensional space. as it is impossible to visualize them in a multi-dimensional space. The offset wells are clustered on this 2D space. These clusters are what we see here. You can change the number of clusters here, which are then recomputed. You can bring context-aware well analytics into your analysis by turning off those properties in the well filtering pane. You will see the clusters are recomputed based on the chosen well properties. So the clusters may not be optimally separated with manually weights. To get the optimum separation of the clusters, you can click Relearn. When you relearn, it will relearn so that certain wells are well separated within the new weights. You can let this come up and see how this works. Great, thank you, Satish. There are a few more features we'd like to show you. Next, in the Pareto charts, now let the Pareto charts come up. There we go. The offset wells are visualized on the performance metric space. In this example, we chose cost per meter versus time per meter. In this chart, you can compare and contrast trade-offs in the design of your wells. In a multi-objective optimization problem, the best solutions are non-dominated and have good performance against multiple dimensions. In this example, the idea is to find solutions with both low cost per meter and low time per meter. Some good candidate wells can be identified by these charts. These wells, and Satish can hover over them, on the left of them, the reference well have a lower cost per meter for a similar time per meter, which means you should be investigating them further as a potential good design choice. Thanks, Satish. Next are the well ranking plots. Perfect. Here we can slice and dice the clustered offset well in different dimensions, such as trajectory, rock type, bit type. You can check the performance metrics on these dimensions for the ideal candidate wells and make drilling design choices. As an example, we are looking at the well trajectory dimension. The wells are ranked by cost per meter for all the different trajectories in the data. Great, thanks, Satish. And then finally are the well casing plots. Perfect. These are the well schematic plots with reference well on the left and then offset wells on the right. You can look at each well selection's dimensions, casings, and other information. In a real-world scenario, you can also include hazard information at each section level, which, when available, can be further used for design considerations. Great, thanks, Satish. All right, let's look at an example of creating a new well. When you're constructing a new well and want to optimize well design based on an offset well, you can provide the specifications of a new well instead of choosing from a reference well, and then conduct similar analysis. We'll start by returning to the Offset Wells tab and selecting Create New Well. And in the well filtering pane, which Satish is showing here, you can create a new well with these 5 properties. The properties are latitude, longitude for location, well trajectory, the field, vertical depth, and measured depth. Along with these, the lithology information with multiple depths can also be provided to conduct the offset well analysis. We're not going to go through the scenario in detail, as you can do pretty much everything that we saw in the other scenarios. All right, so let's get to the really exciting stuff, our Data Explorer. Satish is going to change over to our DeepIQ Data Explorer, which is our generative AI-enabled interface. This allows drilling engineers and other subject matter experts to chat with their knowledge graph and type their query in natural language. All right. So the first thing that Satish is going to type in here is, we want to find out, show me the unique rock types in a well that is named Crimson Ridge Field. You can see he's typing that in there. Now, one thing to point out Because Data Explorer understands your data through the knowledge graph and the structure, okay, it provides. You working, Satish?
Yeah, it's working.
Okay. It provides the IntelliSense to help the drilling engineer. So as the user is typing things in, it understands all the different fields and wells and things like that. Here we can see the results down below. There are 4 rock types in that particular well. Let's do another query. So the second query is designed to get more insights on lithology. So let's show the average layer thickness by field where the rock type is clay. And I'll let Satish get caught up there. We'll run this. And the results are below. So it's really small on my screen here, Satish. So. Okay. I can't tell. Did it finish?
Yes, it finished.
Oh, there it is. Got it. Thank you very much. And so this is showing the average layer thickness of clay in meters. So as we mentioned in the slides, it is important to have traceability in the data. In other words, how did GenAI get to this answer? So Satish will click on the Explain button. And what you're looking at here is how the generative AI model traversed through the knowledge graph to get the exact results. Okay, great. Bethany, can we go back to the slides, please? Thank you very much. So today, because of our time constraints, we've only given you kind of a subset of the features of the application. We'd be very happy to do a deeper dive. If you just reach out to us, we'd be very happy to do that. Anthony, would you mind talking towards the business value of the project, please?
Yeah, sure, Jeff. So, I mean, the benefits mainly for the drilling engineers because, we have so much data, but what the actual data they can access through this is curated and comprehensive. The machine learning driven insights help them design the well in different ways. They help them think about different designs for the well to actually optimize it so we get the best case scenario. We have plans to progress and add to the knowledge graph with different use cases. For example, with this, we can add in anything from subsurface to procurement and the end production as well. Our savings from this that we calculated for business case was around 4 million euros. This is partly cost avoidance and partly cost savings. Things, for example, such as time writing. So the amount of time engineers spend on it goes from weeks down to minutes. And we get better performance from the well at the end of it, and this will be good for our production.
So we'd like to thank all of y'all for attending today's webcast. We'd also like to thank OMV and DeepIQ for putting together this timely and informative presentation. Finally, an on-demand version of this webcast will be made available in the coming days and will be emailed to everyone. Thank you and have a good day.
That's perfect. Thank you so much, Bethany. Thank you, Anthony.